So welcome to lecture 17. So today we're going to start, so last time we looked at the so-called Tier-Patodi-Singer boundary conditions when we have a general adapted operator on the boundary. So I initially defined them for these bisectorial ones, but actually I realized that this assumption is not necessary, so we can really do it for the general ones. So today we're going to start looking at eta invariance, and we'll see the connections between these eta functions and the APS boundary condition. So let's start a new So this should all be maybe, well, I guess in the lecture notes, this will be under the heading, I guess, of the APS index theorem or index theory and the APS theorem or something of that sort. So I haven't decided yet how it'll be. So let's start with first a self-adjoint operator A, a differential operator A on... That's true. That's because I forgot to do this. This is why it's probably a good idea not to be too fancy. Okay, alright, so what's the setting? So the setting is that sigma is a compact, sorry, I should say compact. Don't like the terminology closed, but... So compact without boundary. So compact with the boundary is empty. Okay. And now we want to consider an operator A, which is a differential operator of order 1 on some bundle over this over sigma, which is elliptic and self-adjoint. Okay. So recall from before that the spectrum of A is discrete. Okay, so that means so what does that mean? So actually in this self-adjoint case, i.e. Discrete and only consists of eigenspaces. So we don't get generalized eigenspaces in this situation because we're self-adjoint, right? So i.e. spec of A is something like, so from negative infinity, negative n, negative 1, so lambda 0 is 0, and then we have okay, so this is real now because it's self-adjoint, and so the eigenspaces lambda I are smooth and finite dimensional. Okay, because so that's what we have for a self-adjoint operator. So we have a lot more structure than a general bisectorial operator. Okay. So now let's define the following important spectral functions. So whenever so let's define okay, so for given S a complex number, we define eta A of S to be equal to the lambda in the spectrum of A with non-zero, signum A as lambda divided by lambda to the power of S. So what's this equal to? So this is equal to lambda I equals 1 to infinity of, well, lambda I to the minus S plus lambda I equals 1 to infinity lambda I to the lambda minus I to the minus S, right? So maybe actually I'll just write it like this for the moment. Minus S minus, so the signum changes the sign here, lambda minus I to the minus S, right? So so everything is real here, so this is why we, you know, for the negative eigenvalues we just get a positive here. Okay, whenever it exists, right? So I should say whenever it exists. Okay, so it could be that the eta function doesn't exist for some S. Okay, so why are we interested in this? So let's make a remark just to motivate this. Okay, so consider zeta of S defined as the sum of I equals 1 to infinity I to the minus S. So this is the Riemann zeta function. Okay, and it arises, of course. So it arises. It arises in number theory amongst other areas, and so what's a feature of this zeta function? So the zeta function, it is meromorphic on the whole complex plane, and in fact holomorphic on C subtract 1 with a simple pole at S equals to 1. Okay, that's the structure of the meromorphicity. Okay, so why is this zeta function important? So you might have seen the expression, so the expression, you know, that everyone loves to throw around, this expression of Ramanujan, 1 plus 2 plus 3 plus dot 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 is equal to negative 1 on 12, right? This expression, I mean, this is a sort of a, so it is the formal expression that well, it just, you know, is thrown about, and obviously writing it in this way is wrong, but this is really justified by zeta evaluated at -1. Of course, now we can evaluate it at -1. And if we do that, this is actually equal to negative 1 on 12, right? So this is what is really meant by this expression, okay? So it's a formal expression, but what's really meant is that you consider the zeta function, you consider its extension to the entire complex plane as a meromorphic function, and then you evaluate it at -1, Okay. All right. So the Riemann hypothesis, right? So the Riemann hypothesis says that the non-trivial zeros of zeta occur at the real part of S equal to a half. Okay. So why am I telling you about the zeta function? So let's consider what happens if we have a non-negative self-adjoint operator, right? So suppose now that we have some non-negative, so D's may be a bad choice. So let's talk about an operator B which is non-negative. Self-adjoint. So here we can consider now a zeta function with respect to, so of course it's a differential operator, right? So we're going to have discrete spectrum and so on and so forth in the setting of at least this compact setting. So now we can also consider, just as the Riemann zeta function, we can consider a zeta function which is a spectral zeta function of the operator, and that's precisely given by that expression, right? So this is the spectral zeta function. And it plays an important role in many geometric applications. So this is really so if we look at the expression of the eta function, it takes a very, very similar form, right? So the point is that the eta function, generalizes the spectral zeta function to general self-adjoint, i.e. two-sided spectrum, right? And what is it really doing? So if we have a look at this expression of the zeta function again, I mean, we've excluded the eigenvalue 0. So what it's so suppose that we have a symmetric spectrum, right? Suppose that these terms independently converge and we have symmetric spectrum. It's easy to see from the expression that if we have symmetric spectrum, that precisely the eta function is 0, right? So it's only a non-trivial object if the spectrum of A is asymmetric across 0, right? So what it's really doing is it measures in this case the eta function measures a certain spectral asymmetry. Okay, so in fact, the original paper where this appears due to Atiyah, Patodi and Singer is titled Spectral Asymmetry, right? So this was really the gadget that they were interested in analyzing. Okay, so let's think about how we could possibly study this operator, right? So an outline to study eta A. There are numerous details involved with it, and we'll cover all of these details, but I think it's easy to sort of get lost and not see the forest through the trees. So let's think about how we can study this, right? and what this has to do with boundary value problems. So we consider. So one way to do it is to consider D built out of A, let's just say, i.e. such that A is an adapted operator for D on M such that the boundary of M is equal to sigma. Okay? So we consider some operator D, which is on a manifold where sigma is now the boundary of that manifold. And now that we have boundary, so what do we do? So how do we think about this in terms of boundary? So the idea would be to try and find a good boundary condition say B eta A for D such that D B eta A is Fredholm and sees the eta. Okay, so we have to sort of think about what we mean when we talk about seeing the eta. Okay, so let's think about that for a little bit. So let's rewrite the eta function. So let's rewrite eta of A. Okay, so this is what I wrote earlier. So let's rewrite the eta of A as, so this is going to be the sum of the lambda I to the minus S plus the sum of the lambda minus I to the power of minus S, right? This is what the eta function is when it exists. So let's see this from a spectral point of view, right? So of course, if we have a Fredholm operator, and we have some resolvent for this Fredholm operator, or we construct some sort of operator out of it that has a resolvent, then we have discrete spectrum because at least for on a compact manifold M, so I should maybe say M compact, we'll have that the domain of DB, if it's Fredholm, well, actually we want it to also be elliptic. That way, we're guaranteed that the domain is sitting in H1, and so maybe we move to an operator which has a domain even sitting inside that domain, and we'll see that in a second. So we're guaranteed that if it's something like self-adjoint, we'll have discrete spectrum again, right? So we can try and think about all of these things from a spectral point of view. So let's just try and understand this object from just an operator point of view, right? So for that, I'm going to make a definition that we'll need also for later. So definition. So let S be a bounded operator on a Hilbert space. Then S is said to be trace class if for EK an orthonormal basis for S for H, the trace of S, which is defined as S EK, so some K EK, is finite. Okay. So okay. So just very quickly, so the remark I want to make here is that the trace is independent of bases. In application, it is worthwhile to use a basis arising from the spectral theory of S, right? So that's just a remark. Okay, so let's return back to our eta function. So what do we have here? So recall, so we have that A is self-adjoint. So A self-adjoint means that L2 of the boundary splits into the kernel of A plus the range of A, right? Not range of A closure, because A is a Fredholm operator, right? Yes? Yeah. Yes, sorry, I should have said that this everything here is with multiplicity. Yes. Sorry, that's a very important thing. I'm always counting the spectrum with multiplicity. So really, yeah, I've been a bit naughty there. So I really should have, yes. So so these are really less than equal to's, right? So for the zero eigenvalue, yeah. So okay, we're excluding the zero eigenvalue, but really this is with multiplicity. Sorry about that. That's a very important remark. Okay. Yes? Mm-hmm. Well, actually, it's equivalent. Yes, yeah. So the point is that actually being trace class for S and the trace class for the absolute value of S, these are equivalent. Yeah, yeah. Okay, so so we have that L2 splits in this way, but of course, so we have the domain of A is in H1 of sigma E, which is compact in L2 of sigma E. Right, so sorry, domain of A is equal, and this is compact. And actually, so it's not hard to see. So A is a differential, first order differential operator, which is self-adjoint. So there is a resolvent point. In fact, lots of resolvent. So it's not hard to see that the range of A is closed, right? So it just, in fact, comes from this embedding and the theorem of Hermander that we talked about last time, right? So we just consider the norm and the range of A is automatically closed. And because it's self-adjoint, remember we have this orthogonal splitting into the kernel and the range. So this splitting is what, right? So it's just, so we have eigenvalues, say just point spectrum. So this splitting can just be realized by taking a Conway integral around 0, which gives us a projection to the kernel. So the range of A, so if we consider, so the point here is that if we consider A restricted to the range of A, so this is now going to be an operator from the range of A to itself, unbounded operator, and it's self-adjoint, and then the spectrum of A restricted to the range of A is precisely going to be the spectrum of A subtract 0. Okay? Right. And so so now let's think about the eta function in terms of this trace. So the eta function now at S So this is going to be what? This is going to be taking the trace of A restricted to the range of A, and we take the modulus to the minus S, but now we compose this with the signum of this guy, right? So if we do that, we can see that we pick up the negative and the positive parts separately, and then when we take the trace, we end up with the same expression that we had before. Okay? So actually, we're not going to really use this form for this operator theoretic form for the trace, because, and I'm just saying it here in case you want to think about it in this other way. So the way that we're going to proceed is actually the original way that Atiyah, Patodi, and Singer considered all of this back in the 1970s. So this is a very old theorem, and in fact, in some sense, the desire to study general boundary conditions and non-local boundary conditions for first-order operators really comes out of their study of the eta function, right? So, yeah. Okay, so the idea now is access eta A as an error term of a heat equation. Okay, so that's more or less the perspective that we're gonna take. Okay, so for that, let's just think about a few more abstract facts. So, so we need to think about a few more abstract facts for this. So let T be a closed operator on a Hilbert space. Closed, densely defined. Densely defined and closed. And suppose that T star of T and T star. So now note that T star T and T star are both densely defined self-adjoint operators, right? But we further suppose that these have discrete spectrum with finite dimensional eigenspaces. So this would occur if T star T are compact operators, right? If their domain is contained in if their domain embeds compactly into H. Okay, so clearly T star T and T star are non-negative self-adjoint. So, first lemma. Lambda is in the spectrum of T star T outside of 0 if and only if lambda is in the spectrum of T star away from 0, and the eigenspaces of T star T of lambda are isomorphic to the eigenspaces of T star lambda. Okay. So let's prove this. So, let lambda be in the spectrum of T star T outside of 0. Okay? So what does that mean? Then there exists phi in DOM T star T such that T star T of phi is equal to lambda of phi. Okay? But this is now, okay, so so we already know that phi is in dom t star t. So then again, lambda times this phi is in dom t star t, which is in particular contained in dom t. Okay, so that means that t star t of phi is contained in dom t. So then we take t star t of phi, which is, I mean, we can just write this as t star of t of phi. This is equal to lambda of t of phi. Okay. So what does this tell us? So this tells us that lambda is in the spectrum of t star outside of 0, and the map phi to t phi takes us injectively from t star t of lambda to the eigenspaces of t star of lambda. This is an injection. Okay? That's from the linearity of t, of course. Okay. So so now suppose psi is in eigenspaces t star of lambda. Well, suppose that t phi, so suppose that we have that t phi is equal to t psi. So, okay, it's just the linearity of t and the fact that we're outside of the 0 eigenvalue, right? So, if t phi is equal to t phi tilde, that happens if and only if phi minus phi tilde is in t of phi minus phi tilde is 0, right? So that means that phi minus phi tilde is in kernel of t, right? But we assume that we're in the lambda eigenvalue, right? So that means that phi minus phi tilde is equal to 0. Yes? I mean, these are eigenspaces, right? So we're mapping into some eigenspaces, and then we're saying that actually it's an eigenvalue for t star t of the lambda, but now we have an eigenspace for 0, and these eigenspaces are, well, they're going to be complementary, right? So then we have to get that this is 0. Yes, of course. It's the same as the kernel of t star t, right? So we've already seen that before, I think. But okay, I'll leave that as an exercise. So maybe that's something good to think about. Okay, anyway, so let's suppose now that psi is in the eigenspace of t star, t star. So this happens if and only if t star of psi is equal to lambda psi, which is in now dom t star. So then we do the same trick as before. We look at t star t star psi is equal to lambda t star psi. So that means that's if and only if t star of psi is in the eigenspace of t star t of lambda. Okay, so that means, so that finishes the proof, right? So that tells us that this is actually, this has to be a bijection. Okay, so maybe I should have reversed the role of these two lemmas, because the question that was just asked before about the equality of the kernels, this is exactly what I'll prove here. So maybe we haven't seen this before. So the second lemma, so maybe it's a good idea to interchange the roles of these two if it wasn't clear from before. So the kernel of t and the kernel of t star t are equal. Okay, so this might be surprising, but let's see why. So clearly if I'm in the kernel of t, I'm going to be in the kernel of t star t, right? So kernel of t is contained in the kernel of t star t. But now, so we want to prove the opposite inclusion, right? So let u be in the kernel of t star t. So that means that v equals to tu is in the kernel of t star. Okay? But always we have, recall, so from previous proposition, we have that the Hilbert space is going to split as the kernel of t star plus the range of t closure, right? So we've already seen this from before. So so what do we have? So we have that v is in the range of t now, intersect the kernel of t star, but that's just equal to the 0 subspace, right? Because, I mean, this splitting is exactly telling us that these are complementary subspaces. So that means that u must be in the kernel of t. Or tu is 0, right? So, so tu is 0. And that's the conclusion that we wanted. Okay, so it's not hard to prove that in fact, this is a very important lemma moving forwards. Okay, so why have we talked about these operators t star and t star t? So let me prove another abstract proposition that will help us move forwards. So let f be a continuous bounded function on 0 to infinity. Okay? Then f t star is trace class if and only if f t star t is trace class and the index of t is equal to the trace of f t star t minus the trace of f t star. Okay, so well, maybe I should say, and in that case, okay, so we also get a finite index if we have these being trace class. Okay, so the proof. So is the of lambda, so lambda in the spectrum of the width, oops, I went offline for a second. Okay, so let me just say that again. So because we're counting things with, oh my God. Okay, sorry, I'm back. My system seems to have So someone is sharing a screen. I'm host now. I did. I am just back. Can you hear me? No. Unmute. Can you hear me now? Okay, yeah, I disappeared. I don't know what happened there. Okay, so sorry, we're back. So what did you... So can someone tell me where we were up to when I disconnected? Okay. So so as we pointed out before, or I was reminded before to tell you, because we're counting always with multiplicity, so let's peel away the first part, the zero part, right? Because remember, these are non-negative self-adjoint operators, so we're not going to have any negative spectrum. So we get the dimension of kernel of t star t to begin with, and then we get the positive eigenvalues, right? So f of lambda. Again, taking the sum with multiplicity. Similarly, we can compute the trace of f t star which is going to be the dimension of the kernel of t star plus no? Why would f of 0 be 1? Oh, I see. Sorry, I see. I see. There's a f of 0 here. Yes, sorry. There's an f of 0 multiplied by yes, sorry. Actually, I have to adjust the index formula. This is f of 0 times the trace, right? That's a factor I've forgotten. F of 0 times the trace. So, yeah. Okay, so this is f of 0 times this plus mu. So mu is now the spectrum of t star of f of mu. Okay? So, right. Sorry. Yeah. Is this the correct way? It's f of 0 inverse, right? So the index is, so I should maybe say that I'll put the f of 0 to the other side. F of 0 times the index is equal to this. Okay. Okay. So all right. So so therefore, so from before, from previous lemma, what do we have? We have that the sum of lambda positive f of lambda is equal to the sum of mu positive f of mu, right? So if one is finite, the other is finite, okay? And this is really because the eigenspaces are also isomorphic, right? So any weighting that we get of these eigenspaces, it's going to be reflected in this sum, right? So we have up to multiplicity, and we have that the spectrum is equal outside of 0. Since we assume that the eigenspaces of t star t lambda and eigenspaces of t star lambda are finite dimensional, we have that the kernels are also of finite dimension, right? So the dimension of the kernels are t star t minus plus dimension of t star are finite. So because of that, if either f of t star t or f of t star are trace class, we get that the trace of f of t star t minus the trace of f of t star is equal to f naught times the dimension of the kernel of t star t minus the dimension of the kernel of t star. But by the previous proposition, this is exactly f0 dimension of the kernel of t minus the dimension of the kernel of t star, which, if we recall when we talked about the Fredholm conditions last time, this is the dimension of the kernel of t star is precisely the co-kernel, right? So then this gives us that this is f naught times the index of t. Okay. All right. So why did we go through this detour of trace class and so on and so forth? So as I said, we want to try and relate things that we know to heat kernels. So the ansatz here. So this, it's not a consequence that we are thinking about the problem in this way. So thinking about heat kernels to try and connect to indexes really comes from analysis even for the closed manifold case, right? Even on closed manifolds, when one looks at the Atiyah-Singer index theorem in that case, one takes heat kernel expansions to really understand the index. And so this is a reasonable ansatz, right? So what's the ansatz now? Look for a boundary condition B such that e to the minus t, e to the minus tau db star is trace class. Maybe I'll put d star b here. Trace class for t positive. So by proposition, we have e to the minus tau db star db is trace class. And of course, with this choice of function now, at 0, the 0 eigenvalue is just going to be 1, right? So here the index is going to really be equal, right? So the index now of db is equal to the trace of e to the minus tau db star db minus the trace e to the minus tau db star. Okay, and we've afforded something here because we are now free to choose, right? So this should be tau. So this is true for each tau positive. So we can also choose the tau in a way to try and muck around with expansions, and we only really need to know that this is true for some tau, right? So we afford ourselves with extra tools by looking at a parameter, a family of such operators for which we can recover this index. And then the idea is that, yes? Sorry, this is the wrong order. This one. Right? Is that okay? So the point is that in the proposition, we're looking at operators, two operators, right? We're looking at t star t and tt star. The reason that we're looking at these operators is because t itself might not be a self-adjoint operator, but tt star and t star t are self-adjoint operators. In fact, they're non-negative self-adjoint operators. So we can certainly talk about heat equations for these non-negative self-adjoint operators. So how do we now connect those things back to the index of the operator t? Well, we have to go via this lemma that equates the kernels of the t to the t star t, and conversely and also the kernel of T star is now going to be the kernel of T star, right? So now we have a way of accessing some other quantity, the index, through now a family of operators, which are heat equations, right? So these are really heat traces that we're looking at, and this is affording us with a lot of freedom, right? So we can fix some tau positive, and then we are able to recover the index for all these positive taus, and then we need to just look at asymptotically how the heat traces behave near some fixed value of tau, and that connects us with this quantity which is the index. Okay, so absolutely not. That's really the quintessential feature. So the question was, does the index not depend on the tau? It doesn't depend on the tau by this previous proposition, right? So that's why I wanted to. For every tau, it's a different f, but we have this general formula, right? So that's why I wanted to prove this proposition at this level of generality. So so what is the logic here? The logic here is that we want to afford a huge amount of freedom by going to a large class of tau, but for this large class of tau, we have a fixed object which is the index, and then we go back to, so this is like going to a universal quantification. Now we want to bring it back to an existential thing, right? Because we want to look at this latter object, the tau dB star dB minus the trace of e to the minus tau dB dB star containing eta a for near some tau naught in 0 to infinity, right? So including 0. So maybe the right thing to look at is tau at infinity or tau near infinity, or I should say maybe including infinity, right? So so maybe we need to go out to infinity, or we need to go out to 0, right? Or some finite value. But this affords us with a lot of freedom to try and muck around with this. All right. So that's really the ansatz, and that's really the outlook now, right? So the outlook is to proceed according to this formula. All right. So now let's return back to the operators that we have given by the problem. So let's return back to the operator A, which is self-adjoint elliptic first order. Yes? Yes, it is. This is all a number, yes, because the index is a number. Well, the eta is also a number. Yeah, I mean, look, this is an ansatz, you know, it's not a precise statement. So the idea is to somehow... Well, eta A we can evaluate at each s, and this is going to be a number, right? So we want to understand eta at some s, say. No, it's not a precise statement, right? This is an ansatz. It's not saying that it is equal to this. It somehow allows us to access this. So maybe the trace is some formula where the eta A of S appears, right? As long as that happens, we can try and understand eta A of S in terms of now a boundary value problem that we've set up on a manifold. it's not meant to be a precise statement. I mean, we'll see exactly how the eta A of S connects to these traces, but the point here is that this is an overall, I mean, this is an overarching perspective, right? So the question is, how do we try? Let's say sees eta A of S. Okay, so it sees eta A of S in some way, right? So this is just a broad method. I'm not making any precise statements here. Okay? Well, the point is that the tau 0 will allow us to access the eta A of S. So the tau 0, so the idea is that we have these heat traces. And the idea is that around the tau 0, we can try and take some asymptotic expansions. And it's in these asymptotic expansions, as maybe tau approaches tau 0, the eta A of S becomes visible, right? So all of these things will become clear as we move on. In fact, I can tell you now that really what's happening is that, it's really when we start considering the tau 0, so tau 0 at 0 is really where we start recovering the eta, right? And we'll see that. We'll see all of this. So these two are ansatzes, and we will start seeing all of this precisely as we set up the problem. Okay, but I just wanted to give an overarching picture of where we're going, right? So because now we're going to have a lot of calculations that are going to pop up. So I want to justify these calculations. I want to make sure that we're not just doing the calculations for no reason whatsoever. Okay, so let's return back to the A, which is self-adjoint elliptic first order on this boundaryless manifold sigma. So what do we get here? So this is self-adjoint. So we get that the L2 space, this is going to split orthogonally as the eigenspaces. So this is an orthogonal splitting over the eigenspaces of this A at lambda. And of course, each of the eigenspaces are also smooth, right? That's elliptic regularity for, yes, so this is from elliptic regularity, so this is what we get. Okay, so then for V in L2 over the eigenspace of V, we can write V as equal to the sum over the spectrum of V lambda. So I should say V of X here. So just to clarify this, lambda of X, where phi X is an eigenfunction. Is the eigenfunction, because we are counting with multiplicity for A of lambda. Okay. Okay. So now I want to consider this is the bundle E sigma. Sorry, this is the bundle E sigma. All right. Okay. Now let's consider the bundle E, which is just going to be the pullback. I guess it's a pullback bundle, so you can write this nicely if you like, such that V is in E sigma of X. So this is now a bundle over what? This is a bundle over the cylinder. So let's first have a look at the infinite cylinder. So this is a bundle over the cylinder. Right. Okay, so now if we have a U in L2 over the cylinder landing us in E, we can write U of Tx as equal to the sum, again, over the spectrum of A. but now the u, the coefficients are going to be dependent on t lambda of x, right? So this is, so I'm just doing a eigen decomposition on each slice, right? Because we can write the L2 as an L2 space over the interval mapping into the L2 space over, so L2 over ZE is really the L2 space of the interval mapping us into the L2 space as a Banach valued space over M of E, right? So because of this, we can write out the expansion in this way. All right. Now let's, so now I have, yes, so, yes, sorry. So I should really write sigma here. And then it's not M, it's Z, in fact, right? So I should really write sigma Z. Sorry, this is then for V in sigma of E. Yes, sorry. Okay, yeah. This is a bundle. I'm writing a vector bundle over the cylinder now. Yes, this is now the vector bundle over Z. Okay, so it's just on each slice, it's E sigma. Okay, so this is just a model problem now, right? So what do we have? So now let d naught, let's define this as dt plus a. So this is actually a differential operator of order 1 on E. So over the over this infinite cylinder, and it is clearly elliptic, right? Okay. Right. So now the idea. So what's to come next? The idea. So now let's let me see. So okay. Okay. So what we're going to do next is to equip. So we equip d naught with the, so what's next? So next, so what's to come, so the, well, I should say the idea is equip d naught with BAPS of A, and to obtain d naught APS star d naught APS and d naught APS d naught APS star, right? So eventually we're going to be considering these two operators, which are Laplacians, and we want to also consider the heat kernel. So okay, so let's do that now. So let d naught APS be precisely equal to d naught BAPS of A. Okay, so what is BAPS now, right? So so BAPS. So remember, we wrote this down last time as the negative spectral projection of A with this little subscript A, right? So here we took the smallest eigenvalues and we did a spectral cut. So this is lambda minus 1 and this is lambda 1, and we took a spectral cut so that it falls within the minimum of both eigenvalues, right? That's what our little subscript A was, h½ sigma E. Okay, so this is exactly equal to what? This is exactly equal to the sum over the negative spectral eigenspaces. So because we've got a self-adjoint operator now, we can write it in this way. These are the negative spectral eigenspaces intersect, well, these are the L2 eigenspaces intersect H half, right? Sigma E, that's what we get. So, so in the form that we've written the operator dt plus A, so this is now, we can consider the, so what's the adapted operator for the formal adjoint, right? So the formal adjoint is d0 formal adjoint is equal to negative dt plus A. So that's equal to negative dt minus A, right? So the formal adjoint is minus A. So B APS, so the boundary condition corresponding to this is just going to be the annihilation. So B annihilate the check space now of A D naught from before. So what does this give us? So this gives us okay, so I should say this is multiplied by this is multiplied by a minus here, right? Because we have the sigma, the endomorphism here is just multiplying by a minus sign here. So this is going to give us okay, so actually let me see now. So that's not what I want to consider. Let me just see the best way to write this. Okay, so there are two minus signs that cancel out. So bear with me for a second. We can just write this as an annihilator. And this is going to be what? This is going to be the chi plus of A little a, H half. We'll see why this is in a second. Intersect E. And then this is equal to the positive spectrum, including the eigenvalue 0 now, of the eigenspaces of A lambda intersect H half partial M E, right? So I write this is not the correct thing to write here. So this is really this is the negative sign multiplied by this, right? So really, so negative here really means that we have to flip the sign if we consider the boundary condition for the operator D naught dagger, and then we'll get all the eigenvalues of, again, the negative eigenvalues of A, but now include up to and including the kernel, right? So I just want to give a description of what the APS conditions look like for this adapted for the cylindrical, the model operator that we get from fixing a self-adjoint first order differential operator A on the boundary. Okay, and now the Laplacians we want to consider. So the Laplacians, the associated Laplacians, these are going to be defined as Laplace 1, which is going to be D naught APS star D naught APS, and lambda 2, which is going to be D naught APS D naught APS star. And we want to analyze these two. So again, we want to try and understand some traces of these things, but not on the full cylinder. We want to later on consider this not in the full cylinder, but we want to now understand the traces of these heat kernels, at least near zero, in terms of certain so-called kernels of operators, right? So I want to very briefly talk about Schwartz kernels of operators. So in order to study the traces of e to the minus tau Laplace 1 and traces of e to the minus tau Laplace 2, need to understand kernels, well, Schwartz kernels, I should say, of operators. Okay, so this is the last thing I guess we'll look at today, and then we'll move on next time to analyzing these Laplace 1 and the Laplace 2. Okay, so if you did the microlocal analysis lecture last semester, you would have already seen these things and you would know these objects quite well. So let pi 1 be the projection m cross n to m, and pi 2 the projection from m cross n to n. Okay, projections. Foot point. No, that's not right. It's just projections. They're not bundles, so okay. So we define the outer tensor product of E and F as follows. So this is going to be pi 1 pullback E tensor pi 2 pullback of F, right? Given two bundles, E and F over M and N, right? So given E over M and F over N, we consider this. So so what is this? So this is just a formal way. So what are the fibers of this, right? So if we pick a point X and Y in M and N, the fibers of this are precisely EX tensor FY. Okay, so it's just a formal way of writing this. So what's the Schwartz kernel theorem? So I'm just recalling these things now, right? So hopefully somewhere you've seen these things before, but it's also possible to really intuitively understand all of this. So if we look at distributions over M cross N, E star, in our, so okay, how do I want to look at this? So yeah, so E F. So the map that takes us from distributions to bounded operators, acting from DME to D prime NF, which takes some K, which we call the Schwartz kernel, to the operator T defined out of K. So this is a bijection, right? So in short, what it's saying is that there is a correspondence between bounded operators of this form and these so-called Schwartz kernels, right, which live at the level of these distributions over this exterior tensor bundle. Okay, so I'm just saying that impressionistically, so there's something rigorous here, but we're really, let's think about what happens in our special setting. In our special setting, well, yeah, I don't want to get into it too much because it's just going to become, so it's going to become clear what this map is when we write it down in our setting, right? Because we don't need the full brunt of the Schwartz kernel theorem, right? I'm just about to describe now what these maps are in our specific setting. Okay? So given a k, there is a certain induced tk, and given some operator, there is a k such that the induced thing is of this form, right? But let's not get into the guts of the Short's kernel theorem, because we don't need to really use it to its full extent, right? In fact, we won't be using it at all. We just really need to induce operators given kernels. I just wanted to say that there is such a theorem. If you're interested, please go look it up, but we're not going to require the full brunt of this. The analysis that we're going to do is a lot more intuitive. So in our special setting, what we have is actually what's maybe a good letter for an auxiliary manifold. So let's say that we have P, which is an auxiliary manifold, and we want to look at kernels. So we look at a varying family of kernels that are really measurable sections of M cross M into E star exterior tensor E. And the associated operator to K is given as Tk of U at some point Px, which is equal to the integral M over K P x prime x U x prime integrated against a measure d mu x prime, right? So this is why I didn't want to specify the Schwartz kernel, the interaction, the actual map between K to TK in the Schwartz kernel theorem, because there you have to write it really out in terms of, you know, this exterior tensor bundle setting. But here we have a very, very concrete operator, right? The kernel really arises as a measurable section of a certain bundle. So this is still somewhat not so tangible. So let's really look at it in terms of when we have a basis expansion. So if U is in L2ME and U is equal to U lambda, so some U lambda phi lambda of X, where phi lambda of X is an orthonormal basis for L2ME. And we know that TKU for each P is a bounded operator on L2ME. Then we can decompose the kernel also in a nice way, right? Then the kernel can be decomposed in the following way. So it's going to be K of P phi lambda X prime star tensor phi lambda of X. So what do we have? Phi lambda of X prime star acting on some U X prime is, so now of course our bundle has to carry a metric, right? So I've been a bit slack with defining all of these things, but this is precisely X prime phi lambda X prime, right? That's what this action is. All right. So therefore, TKU at Px is equal to what? So this is equal to the integral over K lambda. So I'm going to assume Einstein summation. I should have maybe said that before. H x prime E U x prime phi lambda x prime phi lambda of x, right, so d mu x prime. So now we can take the k lambda out, so k lambda of p, and so we have in here just the L2 inner product of what? Of u and phi lambda L2 m of e phi lambda x prime. And then this is equal to k lambda of p u lambda phi lambda of, sorry, not x prime, at x. Okay, so it is what you expect it to be. So it's just the kernel, which is decomposed via the spectral decomposition, just acts as a weight to the eigenfunction expansion of the u lambda. Okay,